And it is indeed my pleasure to begin today with another excellent keynote speech from such a distinguished Australian researcher. So Professor Hugh Durrant-Whyte is an Australian Research Council Federation Fellow and Research Director of the Australian Research Council Centre of Excellence for Autonomous Systems of the University of Sydney. Hugh, for over 4 years, was also the CEO of NICTA. NICTA has been Australia's Information and Communications Technology Research Centre of Excellence and has delivered so much benefit in the IT community in Australia, both academically and in its collaborations and deliveries to business. He is also a Fellow of the Australian Academy of Science and of the Royal Society of London. His research contributions are in navigation of autonomous vehicles and sensor data fusion. In robotics, Hugh has developed filtering techniques that many robots today deploy in the context of unstructured outdoor and underwater environments. But he also pioneered decentralised data fusion and proposing that learning is not so much about building models and computing things, but about memory in and enhancing the robotics' ability to learn. And I invite you to have a look at Hugh's TEDx Sydney presentation for some really exciting examples of the actual deployment of robotics in Australia, and just to get an insight of how much autonomous robotic activity is actually already out there and happening, from self-driving motor vehicles, trucks in the Pilbara, to automation of the ports across Australia. Already we have autonomous vehicles working in those environments, much to the credit of Hugh's work. And there's plenty more to say about Hugh, but let's hear from Hugh himself. Professor Hugh Durrant-Whyte will talk to us about machine learning and natural sciences. Hugh.
It's really great to be here today. I have to say the best conferences are ones where you can take the bus, and arrive and then go home at the end of the day. So it's really nice to be here. And actually what I'm going to do is I'm going to have a little bit of fun this morning. I'm going to give you a bit of a story about what I think is interesting in the whole data sciences area. And I think it comes from a somewhat different direction from the normal data mining, data science things, because, of course, I come from a robotics point of view. And robotics fundamentally is about trying to make real-time machine learning decisions based on lots of different streams of information. And it gives you a slightly different perspective about what data is interesting and the kinds of models that you need to build and a lot of other things like that. So this year is my 20th anniversary of being in Australia. And I came to Australia because, it's a big place. It's a long way from anywhere, conveniently located between Antarctica and Asia. And it's the optimal place if you actually want to go out and build robots, because there's no one around to worry. There's been a long history in Australia of building really interesting robots, not in inside environments or in factories, but instead in areas like mining, in agriculture, for defence applications. We have, at the Sydney University, we have our own flight test facilities and things like that. There's so much scale involved in what you can do in Australia that it's really driven the field in lots and lots of interesting ways. And as I reflect back on what we did in robotics, I think about actually all of these problems. Although we have a machine that's flying around or driving around, the biggest challenges are all about data. They're about how that information is acquired by the robot and how it's used and integrated and fused and used to build models of what it is we're actually trying to do out there in the real world. And so what I'm going to do in starting my talk is talk a little bit about the kinds of big data challenges that we have in Australia that are around the kind of natural environments and indeed science environments, rather than perhaps the normal things that one would think about when you talk about data fusion. So here's one. This is one of my favourite places in Australia. This is the Pilbara. So if you go diagonally from Australia north towards Singapore, after about 5 hours you get here, okay? And it's a really interesting place. It's very, very ancient, about 2.5 billion years old. But the other interesting thing is it's about the size of France and it's almost pure iron, okay? So what we do is we dig up big holes and we put it on a train and we put it on a ship and we send it to China, okay? That's the way Australia works. So what's really interesting about these domains, of course, is it's a perfect thing to automate. all right, because it's a long way from anywhere. It's a very difficult environment, lots of interesting equipment, lots of really, really interesting data, okay? And you want to really put all that data together, build a model for what's going on in these places, the geology, the ore, the environment, and so on. And then you want to build big automated vehicles to use those models to actually execute on something. All right? So this, if you like, is the big data challenge, and it's still there in the mining area in Australia. So I wanted to just show you a little bit about some of the technologies and tools that kind of go into it. I'm going to start with this kind of data fusion thing. So one of the biggest things that we've done in mining is to actually build what I think of as a big machine learning data science center allied to the kind of mining industry. And that really involves going out there and taking all the different sources of information that you have in mining, and you can see over there on the left, where you get data from drills, you get surface acoustic waves, you get hyperspectral information, airborne and ground-based data, you've got prior geological information, you've got laser data, really quite diverse sources of information, which typically mines acquire for lots and lots of different reasons. And yet the objective in the end of the day is to bring all of that data together and to build one model of what the mine actually looks like. You see what I mean? It's a big data fusion problem. And by pulling that together, you want to be able to build a surface model because you want to be able to control machines and so on. You want to be able to grow a subsurface model, that is, what is the geology that we're about to mine? So there's a degree of prediction involved in what's going on. And you want to have some idea of the hardness and other properties of that, because that's how you're going to drill it, shovel it, and do everything else with it. So it's a really interesting, large-scale data mining, data analysis, data fusion kind of problem with really, really interesting data as well. So our approach to this, and this is work, in fact, I did well over a decade ago now with a bunch of people for Rio Tinto, is to use non-parametrics, to use Gaussian processes and things like that, because in the end, what you're interested in is trying to understand the stratigraphy or the spatial properties of different types of information. And the spatial data theme is something that I'm going to come back to in a lot of different ways. So, for example, top right up there, you take what's known as the prior block model, which is the sort of thing that geological exploration provides you with. You add to that information that comes from drilling or face scanning. You try and integrate that now into estimating a Gaussian process, a continuous function that will tell you about iron ore concentrations and also other chemical concentrations and perhaps other properties like how hard it is and these sorts of things. So it's a kind of non-stationary problem in general, okay? So it's a little bit tricky. And also you want to be able to estimate multiple different properties from these sorts of sets of data. This gives you an indication of what it kind of looks like to the automated vehicle. So there's a kind of shovel that goes along with it, and they have that internal model of what the ore body looks like. But in addition, the shovel actually has a hyperspectral sensor on it and a laser sensor. And so what it does is it takes that ore body model and then integrates it. You can see that little video at the bottom. And the green bits are low-grade iron ore, and the purple bits are high-grade iron ore. And it basically can then direct the shovel to pick up the right bit for the right truck at the right time. Do you see what I mean? So you can see the sort of interesting pieces of data that go along here. Clearly, there's a whole bit about automation, and although this talk's not really about that, I just want to give you a sense of the scale here. There are automated trucks. There's now 150 automated trucks running 24 hours a day, 7 days a week up in the Pilbara. And to put that in perspective, that's way more driving hours, autonomous driving hours, than anything Google are doing at the moment, all right? And it's in a commercial application. There are autonomous trains. Some of these trains are 6 kilometers long. These are non-trivial things, right? Autonomous drills, autonomous loaders. It's a really interesting operation. Let me show you a little few videos here. Here is a truck. This is a very big truck. When it's loaded, it weighs more than an A380, all right? It's an enormous thing. It's 300 tons and a 300-ton load, 600 metric tons. And you can see how they operate. They basically have lasers and radars. It's conventional kind of guidance technology. Admittedly, this is an engineered environment, so it's different in that sense, but it's still pretty impressive, you have to admit. I think the other really interesting one are the automated drills. And the reason these are interesting is because in your sense of data science, they're really sampling engines as well. They go out there and sample geology and sample hardness and things like that. And you can use the information that comes back from an autonomous drill to effectively incrementally, and we'll see it in this in a minute, incrementally actually build up a geological model, a hardness model, a model for basically what's actually going on in the mine. So I'll just let that play a few seconds so you get a sense of what information. So this bit's done actually on the mine site itself, although, again, it's being pulled back to a remote system now. But the data is actually sent all the way back to Perth, which is about 2,000 kilometres away. And the geologist, you can see, looks at the different properties that are coming back from the rock. He can analyse the different components that are allied to that. and then integrate them also back into a geological model from other data that's going on in the mine. So again, it's a kind of interesting process. This also, if you ever happen to go to Perth, is quite cool because they've now removed as many, almost everybody from the mining operation. And if you pass Perth Airport, there's a big building with a Rio Tinto sign. This is what's in it. This is called the Remote Operations Centre. It runs 13 mines in the Pilbara, and it now also runs mines in Mongolia and in Kennecott and lots of other places around the world. So I think it's really interesting how things are changing. And the other really interesting part is it's the place where all the data gets gathered. Not just now geological information, but maintenance information, human information, lots of other things. And the opportunities for doing data science in this area are really, really fantastic. So again, another interesting area in Australia is agriculture. We often talk here about how in principle we have the opportunity to feed Asia. But the reality is agriculture now is a data problem, right? It's about understanding soils and moisture, about plants, about how they propagate, about how they're monitored and everything else. Increasingly, agriculture is a data science problem, okay? Very, very interesting pieces of data. The question is how you use them, how you control them, and so on. Equally, it's very allied to work that goes on in robotics. This is work of my colleague at the University of Sydney, Salar Sikaria, and you can kind of see the sorts of robots that we're building, and many of them are actually just data gathering machines. They're machines to pick up the information that you might need to actually control what's going on in the agriculture space. So this is one very interesting example, shows you the kinds of machine learning algorithms we're interested in. This is clearly what would now be called a drone. We used to call them UAVs. Has cameras on it, and what it's trying to do is to find a particular type of woody weed, okay? Because what you would like to do is not spray the entire crop, but find individual instances of a particular type of weed, all right, and then spray those weeds one by one. So the machine learning problem here is really to go into these environments, and of course every weed looks different, so there is no common weed, but there are properties associated with those weeds that you can identify and generalize and use those to basically decide what you should be doing in these areas. So that's one application. Here's another really quite interesting one. This is a vehicle called Ladybird, okay, and it's basically for crop row maintenance, and it goes along the crop rows. It finds, again, instances of weeds and looks at crop health and things like that. It actually has a manipulator arm. Unfortunately, I don't have a video of it. Underneath it will then go in and actually electrocute or spray individual weeds, all right, and look at the crop health and so on. So again, an interesting data science point of view. Use that information combined with soil data, combined with other information to do really interesting things in the whole agriculture domain. And this is really very, very valuable for a place like Australia. Do one last example. So you think Australia's big. For those of you from Europe who've flown over the middle of Australia on the way here you think you're nearly there and you've still got 5 hours to go before you get to Sydney. If you think that's big, the ocean area around Australia is absolutely huge, all right? No one has any idea what's in most of it. So again, there's just absolutely great opportunities for gathering data, for trying to pull this data together and build models for what's actually out there in some interesting way. And I want to reference something called the Integrated Marine Observatory, IMOS, which was actually a big facility funded by the government here, which was an exercise in really trying to gather what's called blue water data. So everything from bathymetrics, gliders, and that sort of thing, but also, as far as we were interested, in gathering information from robotics, all right? So being able to deploy robotics at length, at duration, out there in different parts of the ocean, gather those and use those to build models of what's on the seabed, what growth and rate of change there is in the flora and fauna, and things like that. And so this gives you a kind of interesting idea of the sorts of things that we do. So underwater is interesting because there is no GPS, all right? So you've really got to work hard when you try and do navigation, an area I won't go into today. But also you'd like to be able to, there's lots of, you can't just use cameras and overhead things. You've got to be able to use acoustic information. You've got to be able to use chemical information. Again, lots and lots of interesting, diverse types of information. Use that information to try and, you can't see everything because your view is limited, to build up a bigger model for what's going on out there, and then to try and classify that model in a useful way. What are the right habitats? What's changed in the habitat between now and when someone came here back before, and so on. And there are really interesting things going on in the ocean at the moment. As the oceans warm, a lot of flora and fauna that used to exist as far as we're concerned, in the north, you northern hemisphere people in the south, right, are gradually going into colder and colder waters, or waters that are basically being warmed up. And again, there's a huge and interesting whole data science experience to be had underwater, as well as the fact, if you've seen the beaches in Sydney, it's a good place to do research. So when I left doing robotics, I was really, really interested in this whole spatial data analytics scheme. And, you know, when I look at science in general and I look at the kinds of problems that are around there, there's this whole series of problems that I think exist around large spatial data sets, all right? If you think about the geology, you think about a few other things like ecology and marine science, that's really where all the information is. So I started a significant program in NICTA looking at really what we call spatial data analytics. That is, how to bring together a lot of spatial information and make deep models, build deep models out of a lot of different data types, and use those models to make predictions about spatial outcomes in some form or another. So I wasn't allowed to do robotics at NICTA, or I chose not to do robotics, but we did try and look at other projects. And I'm going to talk a little bit about some of these because they really show the kind of principles that I want to get across here in science, which is that what's really important is not just the data, but it's the kind of models that you build from that data and the way that you put information together. So the first project we actually had was extremely challenging. So we're going now from building a model of a mine to building a model of the entire country, okay? And the challenge we had was really to take a lot of the existing public data sets that exist around geology and other sorts of areas and try and build a model of what Australia looks like at a depth of about 5 kilometres, all right? And the reason for that is, at about 5 kilometres through Australia, Australia is a very old continent, there's a kind of layer of granite, and that granite is radioactive, okay? And that radioactivity creates heat, and that heat can be used for energy, all right? So the challenge is to build essentially a model of where those geothermal resources are in Australia. Now, the picture I put up there, in fact, is completely misleading. This was the model of Australia before we started the project, and you will see some bits are red and some bits are blue. But that's not because some bits are hot and some bits are cold. It's because somebody's drilled a hole in the red bits and realized they're hot, and no one's drilled a hole in the blue bits, okay? And therefore, we're going to assume that they go to the average, okay? So my point here is that a big element of this is trying to manage uncertainty and explain uncertainty that you have with the data and the models and these sorts of things. And I'll repeat it a few times. I'm beginning to realize that the real big challenges in data science are actually about small data, not big data. They're for problems where we never have enough data to explain the models that we want. Okay? Those are the big challenges, not big data, but small data challenges. So this is, in a nutshell, what goes on in the geothermal energy industry. You have to take a lot of this remote data. You don't have data at 5 kilometres, you just have surface data, and you need to do that. You need to use that information to predict what's down there. And the challenge is really a financial one. If you want to drill a hole in the geothermal trade, it costs about $20 million for each hole. So you have to get it right, okay? Otherwise, you will lose money. And so the challenge in our project was to take a lot of remote data and use that to build a model of what is at depth before people drill, and to quantify that by uncertainty so that there is an obvious risk associated with what's going on. And we did it in an interesting way. It turns out there's lots of very, very cool data out there allied to deep geology. For example, magnetotellurics. Magnetotellurics is actually the image of the Earth you get when the sun shines through it from the other side. And you can detect it, and you can measure the different effects that the Earth has on that data, okay? So the electromagnetics that comes from the sun. Clearly, you have other data like seismic, gravity, electromagnetics, but another really cool one, which we use quite a bit, is passive seismic. And there's quite a lot of it in Australia. Passive seismic, you just listen for some things like microquakes, or if you want to go a little bit shallower, you actually listen to the sounds of the waves on the seashore and how they propagate through the continent. How cool is that, all right? So you have lots and lots of really interesting types of data. And the challenge is, how do you actually put them all together into one model? And to do this, we actually changed the way that I think geologists think in general. Instead of saying, how do we put that data together, what we said to them was, okay, let's propose a model for Australia, a candidate model for Australia. We'll just make it up, okay? And then we'll use that model and we'll simulate the different sensor responses, okay? And then we'll compare those simulated responses with what we actually measure. And if they're close, high likelihood of model. If they're not close, low likelihood of model. And then we'll just do that 1 billion times. Okay? So what you end up with, interestingly here, is a probability distribution on possible models of Australia. All right? And this is a good way of doing it in many senses because it allows you to integrate lots and lots of different types of data. You can see now adding a new sensor is actually relatively easy. Okay? And in addition, you change the way people think about uncertainty from parametric uncertainty, in fact, to an uncertainty over models where you say, this is the best model, or here are the group of models that best explain all the data you have. All right? And that really makes you think more carefully about these sorts of things. So again, this is a really interesting to Bayesian approach to doing geological and spatial information. It also interesting is a good program management. If you're doing project management here, this is great because, of course, you give each likelihood function to each geophysicist. Here, you produce the probability of data given model for this sensor, the probability of data model for this given sensor, and come back with the model. That's all we need. Okay, and equally, you can go out to geologists, you can get their prior information about core samples, about different geological interpretations and so on, and you can add that information in. And all you as data scientists have to do is to integrate the denominator. Okay, that's a big challenge, but nevertheless. So it really allows you to use all of your data in lots of interesting and different ways, and it involves also this whole process where you can engage with geophysicists and so on. So indeed, we built prior models based on what geologists think about that domain, about core samples. We do have some core samples from 5 kilometers depth, so we understand what they might look like in those contexts, and in particular in a minute, what their properties are, not just the stratigraphy. And so we have that. Equally, we have simulation models allied to each different sensor type. So, for example, for seismic, 2D seismic, you take a candidate model, you try and predict what the seismic measurements will give you. And again, those are used, and you can simulate those. And then we developed, and then what we do, is we produce a posterior over models. That is a probability distribution over potential stratigraphies that explain that data. There's some great code out there now, and part of this, and I gave you a GitHub thing up the top there, that NICTA developed, particularly Lachlan and various other people at NICTA, is this ability to kind of do this model sampling, this MCMC kind of problem, but in this case distributed on Amazon Cloud. All right, so this takes code like we used to have with Stan and things like that, and actually applies it in a cloud environment, which encourages you to do a lot more sampling, a lot more sophisticated models, and actually makes it much more extensible for different scientists. And I'll come back to this a bit later on as well. And this is the kind of data we end up with. This is the Cooper Basin, which is in the central of Queensland. The reason this data is interesting for, I guess, 2 reasons. The first is we actually have ground truth here. So some people have drilled holes to 5 kilometers depth, and therefore we can check whether what we're estimating and what ground truth is really there are actually allied to each other. The second thing is, it turns out there were some interesting scientific discoveries here. We realized this is actually granite that's been weathered during when there was snowball Earth. Do you remember that process that they often talk about? So about 800 million years ago, there was a glacier on top of this, and it actually wore a channel through the granite. Okay, and you can kind of actually see this type of effect in the data that we have, and that kind of really piques your interest because you're now looking at data that's actually being used to do geological discovery. Okay, and I think that whole process is really interesting. And here you can see what we're actually doing is predicting at about 5 kilometers depth the probability that there is granite whose temperature is higher than 275 degrees. All right? So if you're out there now as a geothermal person trying to figure out where to drill a hole, there are some obvious candidate sites. And if you're familiar with geothermal energy, you need to drill 2 holes, connect them together, and then pump water through. Okay? So the other property you should be interested in is whether that rock is going to fracture. So it's actually not good enough that it's just hot. Okay? You actually have to figure out what its properties are as well. This is I will say, an extremely complicated problem. Don't run away with the idea that we've solved it in any sense. All right? But I think there are intriguing techniques here that say, well, with the kind of setup we have, we should be able to estimate these kinds of properties from these kind of rock formations. So this is a different region. This is the Pretty Hill Formation in Victoria. So that was a really interesting project because I think it showed us, to a degree, the kinds of things you could do in terms of integrating a diversity of data, creating quite complex models of complex things, okay, and using those for actually making new discoveries, all right, and of some value. And you can kind of see where I'm heading with the whole data science bit now. So there were lots of spin-outs from this project, and here is one that I think is going to have a profound influence in lots of different areas. So part of bringing all this data together was to make the portal open. That is, so everyone could use all the geological information that we had and be able to apply their own machine learning algorithms to it. And a little bit way down the line, NICTA developed this tool here, which if you've got a computer on you, you can actually log on to now, called nationalmap.gov.au. It is actually just a data portal, so it doesn't have any data. But what it does do is it links to about 50 government agencies that all have data, and then they all have APIs on them, and then thousands and thousands of data sets are all made available through this portal. And it's a really enabling idea, okay, in the sense that unlike people data, which tends to be private, spatial data doesn't tend to be private, right? And so government agencies, private organizations, and this sort of thing can now make their data available through this. And you can see here, it's got everything on it, from the geology to the NBN availability to tax statistics to where park benches are and these sorts of things. You can see here where airports are overlaid on top of tax statistics. So you can kind of do any kinds of now analytics on top of this that says, okay, so what's the price of real estate based on these sorts of parameters? Completely open spatial data. You see what I mean? So I really think that not just in the science areas, but in the social areas and lots of other places, this kind of use of spatial data is really going to begin to take over. Here is one application of that spatial data portal, and this is a sort of follow-on project, which is even harder than the geothermal one. We've been arguing about in New South Wales about coal seam gas. So these are these fracking and everything else that's been going on in the US. And at least at the moment, it's not really allowed in New South Wales. And part of it is not so much the fracking process, but the water contamination that could result for agriculture and things like that. So we had a big project to effectively try and predict what all of New South Wales aquifers actually looked like and what would happen to them if holes were drilled in them. Do you see what I mean? So here now, in the spatial data context, not only do we actually have some fairly complex geology, but we have the fourth dimension of time, all right? And you have to understand how water flows through these systems and so on. And this really brought us to some interesting understandings in general. Firstly, this adding of the temporal dimension means that you must go out there and use real differential equations as part of your data model, right? So if you like, simulations to some degree, and I remember I had this conversation with someone last night, are actually simply another form of data, but they're data that represent different people's opinions, which are just as valid in some sense as actual measurements that you make. Do you see what I mean? So when you build a model, you need to kind of incorporate those. The other thing we really got to at this point is the sparsity of data. I can tell you there is not, by the time you build a model the size of New South Wales and you take 2,000 sample points, which are bores, right, water bores, you do not have a lot of data in which to base your model. And so being able to build big, complex, uncertainty-qualified models with not enough data, small data problems, right, are really what are the biggest challenges in this whole science area. So we learned a lot about how to do that. The other thing was to understand that there is no one good model. So I try and explain. At a New South Wales, at a Sydney level, there's a kind of basin of water, okay, and you can think about it at that level. But is it going to contaminate if you drill a hole here? Well, that actually depends on what happens at the meter scale. If this piece of rock is porous, it will affect things. But if it's not, okay, if it's what's called an aquitard, then it won't. And so you need to understand modelling, if you like, of not just averages and means, but much higher order properties associated with the statistics of things like rocks. All right? So the texture, if you like, of rocks is important as well as their statistics. And I think this was something that was not obvious to the community as a whole in terms of how you would go about modelling and using data. So again, an interesting discovery, as part of doing this. We integrated the application of this on National Map. So this gives you a very good example of we took actually standard existing data about weather and basins and everything that were already in the map, and then we added private data. You'll see at the top there it says Santos bores. Santos is an oil company, all right? So they could take their private bore information, add it to the public data, and then we can compare their private borehole information with the model that the government had accepted as the model of the basin. Do you see what I mean? So you can really do side-by-side scientific comparisons. You can see that the data is actually not particularly well aligned, all right, which should worry you, all right? But it shows you basically how you can kind of bring this information together, again, not just for doing discoveries, but actually for some social, for some public good as well. And it's a theme I'm going to repeat and come back to. We've applied this in other areas. This is, again, this is a sampling problem. We were asked to, by South Australian government in this case, to pick the wells that we should sample in order to get the best model of the aquifer. Do you see what I mean? So they can't afford to go out there and look at every single borehole. And so the issue is what numbers of those boreholes should they pick in order to maintain the variance on that estimate as to what they have. So this is an interesting real-time sampling problem using some fairly complex models. And very, very briefly, one last much simpler application, but very effective as well, was we applied it to doing this, and people have been talking about it everywhere else too, this sort of air quality modelling. The Hunter Valley north of Sydney is a big coal mining area, and so it suffers a lot from dust, depending on the rain, depending on the wind and that sort of thing. They've actually got 14 monitoring stations out there. But, of course, you can use something like a Gaussian process to actually predict what's going on between the measurement sites. And if you've got a proper temporal model, like the water models I've been talking about, you can actually take those and make predictions about what the pollution level will be 24 hours ahead, which means you can actually do something about it. So we produced a model that basically takes that data and, using a lot of historical information, has a sufficiently complex model that it will do a good job of predicting pollution levels 24 hours before they happen, based on weather, based on wind, based on prior experience, and a whole range of other things. We also now provide that actually as a phone app. So in principle, you can now go around with your phone and predict if you have asthma or these sorts of things, or there are remedial things that you can do at a mine in order to basically use that information and look at what's going to happen in the future. So I want to take all that now and apply it to the whole science discovery problem. You can kind of see where I'm coming from now. I was really interested in how data, machine learning, and these sorts of things could actually, and I have a bigger vision, which is probably, I can say in this audience, but not in front of a group of physicists, which is, calculus transformed physics. And yet I look at what I call the narrative sciences, ecology, medicine, and so on. And to be honest, calculus doesn't work in these domains, all right? Because it's just too complicated. There are lots of systems of interacting systems of things that you never really had a good model for. But it could be that data science and machine learning could provide the tools that calculus did for physics, but for these science domains. All right? We do certainly have the tools and the insights to make this happen, and we have certainly talked about data-driven science. Although I will say, and I look at these pictures up here, it's not about big data. It's not about petabytes of data. It's about the way that data is put together to make interesting models that really is the big driver, okay? But if we can achieve that, then I think a transformation in the way science is done is possible from the people that are in this room, okay? That's my big message today. So we have a really interesting project called Big Data Meets Natural Science. It's about 2/3 of the way through now. It was funded by the Science Industry Endowment Fund in Australia. And it really tries to bring together people who do machine learning from NICTA and myself and Circa with people who do natural science from Macquarie, from Sydney Uni and so on, to really try and explore this whole paradigm, okay? What can data science do for science in a really model-driven predictive discovery kind of way? So we're doing a bunch of different things, around data management, which turns out to be a big issue. We're doing a lot of Bayesian stuff, but that last line down there, I guess, is the big driver, at least for me. It says, can we use data to really build predictive scientific models? And if you think about it, discovery is an ability to build a model that predicts something you've never seen before. All right? And that we certainly potentially have a handle on. So we do this in a project-oriented way. So we've actually got 3 projects, and I've realized this is a really good way of trying to do science. We work with the ecologists at Macquarie, and we're interested in things like forest competition, diversity, and how ecologies work. And we're also working with a group at Macquarie to do with laser physics and trying to predict chaotic events in lasers. And we're working with a group at Sydney University trying to predict, or not predict actually, retrodict plate tectonic motions. Okay? So very, very good scientists, top scientists in the field, allied to the data scientists, really trying to address these sorts of things. And for those of you who are interested, and I got to do an advert at this point, we have a panel this afternoon, Katrina and I, which brings together, in fact, a couple of the scientists from these projects and a number of other people to discuss really whether people in the KDD community can drive science in this way. So here are the things that, again, I'm going to talk specifically about some of the projects, but there's definitely some common themes emerging. And I think the first theme is it's about small data and big models. It's not about big data. It's not about petabyte science. It's not about genomics and all these things that you hear about, which are really just number crunching. It's about how you use relatively sparse data to build complex models. Certainly, in all of these applications, the tradition is to have some fairly nonlinear differential equations, and they describe what goes on. And if you were a traditional scientist, you'd use those to predict the outcome of an experiment, then you'd get some data and you'd calibrate those equations. All right? The problem is, what you see is that those calibrations predict only the experiments that you've just finished, not the ones you're about to do. The models just aren't rich enough for that kind of problem, okay? So there's a lot of interesting things, like I've been showing you, of trying to produce probabilities over models, all right, and being able to use non-parametrics to really build complexity into the models while you're doing it. So Models also turn out to be very expensive to evaluate. These are quite complex systems. So if you're trying to simulate the Earth, taking one sample is actually quite an expensive thing to do. And so you want to be a lot more data-driven about the way that you use these models. The final point that I think is interesting that sometimes we ignore is that actually data is very expensive. You know, I showed you in the geological case, all right, if you want to get a drilling data point, it costs you $20 million for a 1 point. Okay, it's a bit cheaper in some of these, but nevertheless you need to go out and measure trees, or you need to measure paleomagnetics, or these sorts of things. It's not a trivial thing to do. It's not a lot of, you know, you really have to work to get the data. So you need to be careful about how you use it. I repeat again, a small data, not a big data problem. So let me talk about plate tectonics, and I have to say in my next career I'm going to be a geologist. It's way more interesting than computer science. You know, I'm sure everyone's familiar with plate tectonics, you know, the fact that the plates have moved. What you're probably less familiar with is that we kind of only know what really happened back for about 150 million years, okay, which is not very long in a geological sense. So Australia used to be part of India and Africa and South America. We know that much, okay, and then it's been gradually separating, and 40 million years from now, Australia will be on the equator, okay. What, though, is really interesting is what actually happened about 1.5 billion years ago. And the reason it's interesting is that's when most of the mineralization in the world happened. And mineralization happens because you get you get an increase in the amount of oxygen, okay? And that allows things like gold and copper and things like that to precipitate. And then you get water, and water allows that to flow through it, and that creates the mineralization. So, and it turns out a lot of these things happen at plate boundaries. Are we getting the picture now? So if I could really predict what's going on with the plates 1.5 billion years ago rather than just 150 million years ago, I'd be a very rich man, okay? So this is kind of, if you like, the Facebook version of science, right? So how do we do that? Well, again, we're trying to do a number of different things, and I won't say this is complete in any sense, okay? We have data which is related to hotspots. So you can see even in these the way that hotspots have moved over a period of time. And this, in some sense, gives you an absolute coordinate frame for where the plates actually move around. Because otherwise it's not obvious, you know, which bits are moving over the mantle. Equally, we've got information like gravity data. We have what's called paleomagnetics. That is the way that the magnetic field has changed in different rocks as the poles have switched around over a period of time. And there's also other things like chemical data. But the first thing you should see is there's not a lot of data. Although that, you know, there's a few spots on here, but I mean, you could count those, okay? There's not that much data in here either. And yet you've got to build a fairly sophisticated model, and you've got to predict back a long way. And so it is really a modeling issue. So we put a lot of effort into trying to build better models for plate motion. And again, using the same sort of thing, instead of having a differential equation, which you use to model magma and which you use to drive a plate tectonic motion, what we're actually doing is using an allied model and sampling it. Again, getting a probability over different types of motion parameter. And that allows you to both qualify the uncertainty that's involved, but also, again, to integrate all those different types of data and any other data that might or might not be relevant, all right, to get the best possible model of what's been going on with the plates. Lots of different sort of things like that. We're also exploring much more spatially constrained ideas using things like conditional random fields that might actually explain how different parts of the plate actually connect together and different things like that. And you can begin to see that, you know, okay, we're not quite there yet, but we could really make some serious contribution to the science of plate tectonics in this area, applying the kinds of tools that you guys already know quite a lot about, and that could actually have some really important economic consequences. I want to mention and advertise here the work of Professor Dietmar Müller, who will be at our panel, who's actually one of the most, I would say, computer-literate geologists I know. And he's got, in fact, a nice open source data portal where you can log in and you can sort of play with your own data, use their data, do plate tectonics motion, integrated with Python. How good is that for a geologist, all right? I think we owe it to him to do some work in this area. So I think the other one that I really find very interesting, although the more I learn about it, the more I realize how little I know, is the whole ecology space. And again, there's been a lot of government programs, both in Australia and in the US and other areas, going out there really trying to gather ecology information. So there's a world portal that you can see up there that really looks at things like tree diameters, where they are, and these sorts of things. But don't forget, sampling the data is quite complex. You know, I mean, although you can get satellite imagery, which is the sort of overview, truthfully, you've actually got to go in there with a graduate student and with a tape measure and measure every tree. All right? And then you have a time sampling thing. How does it grow? And so it's not like you can get the data tomorrow. You really need to look at it over the next 30 years, ideally the next 300 years, to really get a sense as to what's going on. There's some good work going on in the US around gathering this sort of information in particular plates. I will say it's been a bit of a surprise to me to understand how poorly ecologists keep their data. And I think, again, the KDD community could really contribute a lot in terms of the way they simply manage and store and use and make their data accessible. They're not a very open data environment, which surprised me when I started working with them. Equally, over there at the left, they've actually got some really interesting predictive models. So they build these models that say, how will trees evolve and how will they compete with each other? So you've got other data, which is really around, if you like, trying to predict, using differential equations, the kinds of things that you should see out there in the real world. So this is typical, and this is work, again, of our collaborators at Macquarie, Mark Westerby, Rich Fitzjohn, and Daniel Falster. Daniel will be at the workshop this afternoon, and also people from NICTA. And this gives you the kind of idea of what ecologists think about. They have lots of different hypotheses, for example, about how different pieces of ecology, trees and things, might cooperate. In fact, they talk about something interesting, I don't know whether people have heard of it, called the periodic table of ecology, which really sort of makes you think about how different species come together to make stable compounds, stable ecologies, do you see what I mean? And how you can predict those, and how you predict what's out there in the real world, and how you use that real world data to come up with other sorts of hypotheses about how different traits compete and things like that. Because in the end, what you really want to understand is how this is going to change over periods of hundreds of years. We know we're going through a period of climate change. What does that mean for the stability, the fitness of different types of ecology traits and so on? So they have differential equations, that bottom bit there, that kind of say if you have this trait, this would be your life history. Those different traits that interact with each other, some of them survive. That gives you a fitness measure, and other ones will not survive. And the issue is, how can you predict that? So I have to be honest, when I first came to this problem, I'd hoped to do the kinds of things I've been doing with geology. And then about a year in, I realized it was going to be too hard. We couldn't build models of this. It really was very complex. And I think it's still a big open question as to how you build a model of ecology, all right, using data, and use that to really predict right from data what that ecology might look like in the future. That's a big challenge out there, one of several I'm going to mention today. Instead, though, what we do is we've been working on trying to build much simpler models and using those models to reduce the number of experiments they actually have to do in order to come up with different types of hypotheses. So this is, if you like, sampling different types of trait species, looking at fitness, looking at different ways that we can help them in their processes of ecologists of actually using these models. I find it really interesting trying to understand, you see the picture up at the top there, these forest competition models. You know, we often do optimization and we wonder whether it's convex or not, but actually in many of these models you're trying to build a model that itself is not complex, so that it has multiple peaks, because those multiple peaks are actually different species that cooperate together. Do you see what I mean? And you want to understand how those different species actually work together and how they are, each of them, the right solution for the same problem. Do you see what I mean? So there's some really interesting and complex things in here. We've worked very hard on trying to build computational models of these processes, of how to search and predict what these different fitness things look like, what the different traits are. Two sorts of approaches, and I will say we're only, like I said, we're not at the end of this project by any means, is really to try and take the space and do active sampling over the space of different traits so you can reduce the amount of experiments. And the other one is to actually, again, use non-parametrics in some sense to predict the kinds of things that you should be seeing from these different events. So it's a really cool and interesting area. I think ecology of all sciences, in my view, the ones I've looked at, is so data-driven. There is no possibility of us writing down a differential equation which will predict the world's ecology, right? But we ought to be able to gather data and use that data to make a much more data-driven prediction as to how our ecology evolves and so on. So I want to talk a little bit about the future now, say a couple of words. I've recently moved back to the University of Sydney, and I've decided to make the rest of my career about using data science to progress science in general, to try and change the way that we do discovery. And there's a couple of points, and I'm going to talk about a couple of current projects that we're looking at. The first is there is an enormous amount that this community could do to actually simply help scientists access and visualize and use data. I have to be honest, with a few notable exceptions like Dietmar, the science community is in the Stone Age. You know, it would be progress if they moved on to using a database. Okay, and so I think there's a real opportunity for the community here to actually be engaged in helping science become an open data kind of thing, where wouldn't it be great to have one model of the world in which all science data existed in one portal? Think of the kind of co-discoveries that you could potentially make through that process. I think the other thing that's interesting is how you apply a lot of the kind of federated analytics to these. So a big element of it is the data, and many of the problems we look at has to remain on the server where it's actually there because it's just too big to move. And you want to be able to send analytics to data, recover some partial model likelihood, things like that, and then be able to reconstruct those sort of outputs. So I think there's some really interesting bits in that. But the key challenge is what I think of as scientific discovery. I'm really trying to think about the whole scientific method, the standard scientific method of hypothesizing and testing, and what that would look like in a data space, all right? So again, I've talked quite a bit about models and structures, so using things particularly like non-parametrics to build models which build their own complexity, all right? I think one of the failings in some of the things that have been going on using data in science at the moment is to predict one model and then attempt to calibrate unknown parameters. And that is, in some sense, doomed to fail for many of the kinds of things that we look at. The other thing is trying to make inferences. So again, MCMC is one part of it, but I think there are lots of other techniques out there that could be applied to this. And this other thing, hypothesize and test, which is really allied to the whole experimental design. So we intend to push this forward through actually a couple of projects that we're trying to get underway at the University of Sydney, and these are really just thought experiments at the moment, something for the younger people out there in the audience to think about. And I'm going to talk about, just very, very briefly, one overhead each, about each of these. Here is one. This is called the Uncover Project. When you look at Australia, and I might click to the next overhead, what you see, in fact, is that over in the west is actually very old. And in fact, Australia was formed a long time ago by some old bits coming together in the west, okay? And that's where all the iron ore is and things like that. And then in the last 50 million years, Australia's been moving over a hotspot. And so the east coast, which is where Sydney is, has been pushed up. So you can see all the sandstone, right? And basically that was underwater until fairly recently, 50 million years ago, okay? And so gradually that's been pushed up. And then in the middle of Australia, okay, that's just sand. So if you flew over, Katrina was saying it just looks like waves of sand everywhere. No one knows what's underneath it. Okay? So the challenge in Uncover is to figure out what is underneath Australia in the middle. And if you look, just to show you what this is, the dots there are where all the mines are in Australia. And the astute student will notice that all the mines are where we know what's on the top. Can you see that? And there are no mines in areas where we don't know what there is on top, in the middle of Australia. So the challenge is really to take data, and you can see where some of the aeromagnetic information is, all right, that actually predicts that there are these structures that continue underneath, all right, the regolith that exists in the middle of Australia. And undoubtedly, there's as much mineral resource in the middle of Australia as there is at the edges. It's just no one knows what's there. So the challenge is basically to pull that information together, all right, and predict what there is in the middle of Australia, uncover. So that's a really interesting problem, and I think with the kind of tools we've been showing you, you can see the kinds of techniques that could be applied to doing that. It's not as easy as I'm making it sound, I will tell you now. There's lots and lots of complicated things to do with the way water works and things like that, and the history of sort of thing. But again, many of these are just additional sources of information to make this kind of thing work. All right? So a really interesting, provocative challenge. This is another one I've really become tremendously interested in. It's the thing of the future is basically the fact that we are eating too much of the wrong thing, all right? And our genetics are not able to cope with it in different ways. And we are, getting obese, not too badly, I hope, and we're getting diabetes and we're getting heart disease, and they're all related to that. So the issue is, if you go to, and I work very closely with a guy called Stephen Simpson, who runs a very big research centre at Sydney University, and the goal of that research centre is to understand human metabolism. And human metabolism is really interesting. It consists of lots of quite complex pathways, and those pathways are only partially understood in lots of different ways, but you know that they are pathway problems. It's not just one point with an outcome, it's the way that point interacts with lots of other things in that pathway and the way they interact with other pathways. And that's the first bit. The second bit, of course, is that 90% of the human gut is not human, right? It's all got bugs in it that have their own ecology going on. There's a picture of a whole part of them up there. And in fact, the way we digest things, the way we control our, metabolism and so on, has very little to do with our own genes. It's got a lot to do with the genes and the dynamics of the bugs in our gut. All right, so building a model of how those might all come together is another part of it. And then a third part is the fact that actually you read every day, you pick up a newspaper, there was one this morning, and it turns out that what you used to eat now no longer is good for you, okay? Or what you had just given up because you were told it was bad for you, like eggs, all right, now turns out to be just fine, okay? There is a lack, if you like, of connecting all the data points together around the environment, about what we eat, which really makes us understand how these sort of all come together. So you can see there is lots and lots of data. It's still small data, okay? But we need to be able to take this data and maybe build something like a model of the human gut, okay? And use that model to predict down in the lower right there whether I'm going to get cholesterol and whether I'm going to die from it, okay? And wouldn't it be nice one day to have on a doctor's bench something that really says, this guy, because of his history, because of what he's been eating, because of his bugs in his gut, will have issues in 5 years' time. So why don't you start treating him now? Okay? This is a really interesting area. This is not about genetics. It's not about what we think about when we talk about data and health, but it's a lot more diverse. It's a lot more about building complex models, all right, and how those models relate to data. That's a really cool and interesting big challenge. The third one, which I'm very interested in, is trying to build a predictive model of human behavior in some form. And one that I've become very interested in is, I don't know whether people have read it, is Steven Pinker's book on, it's called The Better Angels of Our Nature. I recommend it to everyone. And it won the Pulitzer Prize, and it's a history of human violence, okay? And it really goes to try and explain how the neuroscience, the behavioral, the psychology of people has been changing, even over recent history, and how you combine that with other impacts like how we were brought up, you know, and so on, and how that actually helps you predict what perhaps people will do in the future. I'm working quite closely with a group of criminologists, and just for your amusement, one of the comments the lady made was that, you know, academics would make very good criminals. It's just that we were brought up nicely, okay? We have the right mindset, the right psychology, everything else, and the difference is the way we were brought up, from the womb upwards. And so how would you intervene to kind of reduce criminology in the future? Do you see what I mean? That would be a really interesting challenge. Again, very diverse data types, everything from psychology to environment to behaviors, these sorts of things, and an opportunity to really create interventions that make a difference in that sort of model. So again, I think of it as a physical, as a life science, as a social science endeavor in data science. So I want to end there, but I think what I wanted to really say is there is a great future out there for data science, for people in the KDD community, that says we can transform science, we can transform the future. And I will say I hope that even the last 3 projects that I put up there, the 3 ideas I put up there, are significantly more compelling and interesting sometimes than being able to sell adverts on a mobile phone, all right? And I do encourage the community here, all right, to think differently about what us as a community, as data scientists, can do to transform this planet. Thank you very much.
So such a exciting and motivational presentation this morning. Thank you so much for that. And I hope many of you are inspired to think about the other opportunities there are in analysing the data that's out there that's going to improve human society more broadly. So we have an opportunity for just 1 or 2 questions, and we have some microphones around the place to go to the questioners as well. Do we have...
So some of the familiar ways that a machine learning person gets used to the tools of the trade is this familiar pattern of take your data and now you have a training set, a validation set, and a test set.
Yeah.
In the small data environments where you're looking at, and particularly when you're dealing with these incredibly powerful models like a Gaussian process, what kind of advice would you give someone to proving the effectiveness of their model where they don't really have the budget to split up and ignore half of it for the sake of having a held-out set?
That's an extraordinarily good question, yeah. We used to have terrific angst when we were first doing those GP models for the mining example I showed you at the very beginning. And unfortunately, we had a very willing client, and we really would, you know, eventually we figured out we didn't know what we were doing. Do you know what I mean? We were building GPs and we had no ground truth. And so eventually we said, okay, let's start again. Let's start with this mine. Let's make a prediction, then let's do the mining, and let's go and see what was actually there. Do you see what I mean? And this is a many millions of dollars one experiment kind of thing, all right? So we took all that, we had to do this more than once because we didn't get it right the first time. We realized, like I've just been saying, actually we should have taken all the measurements first. We didn't. So we'd take all the measurements we could, drill the holes again, make a prediction, blow it up, look what's there, do you see what I mean, and do it. And I agree that's a very, very expensive thing to do. So when I come to the geology ones now, or some of the other ones, the biggest thing we can do is actually to get some of the real data out there in the public domain that people can actually use as a proper test trial set. Do you see what I mean? So again, when we were originally doing the geothermal project, we got to the point and realized, okay, we could make all these predictions about what's going on at 5 kilometers depth, but who's to tell whether we're right? Do you see what I mean? Because it's almost a contradiction in terms. And then we chose to go to a particular location in Australia because the oil companies had already drilled to that depth. Do you see what I mean? And we had some ground truth, and we had some sort of thing, so we could, if you like, try and at least approach getting a validation like that. But what we really wanted to try and do with that also was to, and this is what drove us, was to now take our data and make our data public, completely public, so that if someone else came along with a different approach to the same thing, there was data that they could validate against. Do you see what I mean? And I will say it's a bit worrying in the science community that they're not very good. The physicists are good. Let me back off. If you're doing big data like particle physics and astronomy, then that data is typically very good to get hold of. But if you go to like ecology, it's been, one of the people we work with, Daniel, even recently put together probably one of the first papers that really actually combined 4,000 trees data sets together. Do you know what I mean? And ecologists don't naturally share it. In fact, they have a slightly different model than what you'd imagine. They spend their graduate years gathering data. Once they've gathered the data and they graduate, okay, they then write a mathematical model for it, and then they spend the rest of their career exploring the mathematical model, which is not what we should be encouraging them to do. Do you see what I mean? We should be, as data scientists, making that data open, trying to figure out the right kind of testing techniques, like you were just saying, and I don't think I've got all the answers at all, so that they become data-driven scientists in that sort of way. That's not a very good answer, but you get.
So you mentioned a lot about how building the complex model is really helpful in this domain, right? So in a lot of our real situations, because we have a lot of data on the web, in the internet, it actually a lot of times the machine learning model actually doesn't really matter. It's really the features that you come up with. So how do you see that we can, all this complex model, all the intelligence that goes into building these models can actually be leveraged in the other big data areas like internet applications?
Yeah, that is interesting. I mean, it took me a while to work out that actually we're almost solving a different problem here from what people in the internet big data area are, if you see what I mean. Because I agree, when you have a lot of data, more data than you have complexity in the model, all right, then actually very different techniques apply in the terms of the types of complexity you need to actually put together. Whereas when we deal with stuff, you eventually figure out we don't have. Every application, even health, you've got no data. You've got virtually no data at all in some cases. So you need to put a lot more emphasis on it. There's probably a middle ground. I can see a continuum. All right. If you want to now take your data, even though you've got a lot of data, but build a model of something whose complexity is potentially infinite. For example, human behavior. Then you probably still need to, even with a lot of data, use the kinds of models that I've been showing you, because there's just so many infinite ways that you could interpret what a person's behavior might be like. Do you see what I mean? So if I think of the criminology one, in principle we could track Twitter feeds, we could do all this kind of stuff and get lots of data, but the reality is it doesn't show us much about other types of behavior that person may have that in the future may be more predictive than just the kind of other internet data that he has now. Do you see what I mean? So again, I'm quite a fan at the moment of trying to, in that instance, pick that thing of creating probabilities on models. So instead of saying this is the person and these are the uncertainties in how he'll behave, what I'm going to do is to predict the behavior of every, have an infinite possible set of behaviors and sample them. All right, and then I have a different prototypical humans, if you like, and I'm going to basically then sample over the space of those, and there may be then I would be able to say that that person has particular properties, but in this area he may have a whole range of different things that I'm not aware of. See what I mean? And that would be a really interesting way to go with the kinds of data that you have in the big data, much more internet type of things. It'd be interesting to explore.
And one last question.
So in the physical sciences, often you have information that comes not in the form of data, but in the form of constraints.
Yeah.
You know that densities have to be positive. You know that scaling relations have to hold. And a lot of the work in physics, for example,
Agreed.
involves taking those constraints so that you've got the smallest possible set of models before you start doing experimentation. I wonder if you could comment on how you see that playing in some of these more complicated situations like the criminology or the ecology situations where you again have a small amount of data but a very large model space.
Oh, they're hard questions. One of the things I'm trying to push at the moment is the fact that things like that, constraints and even differential equations, these sort of things, are themselves just data. You see what I mean? They may not be observational data, but they're data nevertheless. And we should be able to treat those in the same way that we treat observational, physical, grounded information in terms of the way that we would build a model from combining that with other things. So in constraint, and I don't know that this is the right answer, so don't run away with the fact that I know what I'm doing here. I would either incorporate a constraint, literally as a piece of prior data. So in the prior model, the way that I was showing you, we incorporate prior stratigraphy information or prior other sorts of things, or potentially to actually model different theories as different likelihood functions. Do you see what I mean? Often when you do get constraints, there may be, in physics you certainly get strong constraints, but in what I think of as behaviors, you get constraints which are actually more opinions than anything else. Do you see what I mean? And you need to be able to keep those as part of the whole data fusion thing as well. And opinions and simulations are actually a very valuable form of information for places where you don't have a lot of physically grounded data. Do you see what I mean? As long as you're aware how those actually impact the solution. Look, it's an interesting problem in general. Yep. We talk a lot to the astronomers at the moment because you think astronomy is kind of like understood, but actually they don't also know what they're doing. It's really good. So, for example, they do these big wide area surveys of the sky because actually they don't really know a priori what they're looking for. Do you know what I mean? And so how do you predict in all that data what they should be looking for?
Okay, we must bring the session to a close there, but thank you very much and thank our speakers.
Thank you.